Can you hear us? Okay, so good afternoon, everyone. This is the very last presentation session of BDA 2024. I hope every one of you have enjoyed the conference. So we have 4 short presentation in this session 8. So first presentation is from IIIT Kottayam, and they are going to talk about predictive big data analysis for supply chain management and demand. So we will start with that online presentation. Yeah, can you please
if you can just confirm if my presentation is visible.
Yes, it's visible.
Today I'm here to present my paper on an efficient predictive big data analytics for supply chain demand forecasting through ensemble learning. First of all, thank you for 12th International Conference of Big Data and Artificial Intelligence for this opportunity. Also, my project mentor, Venkateshwaran, and Indian Institute of Information Technology, Kottayam for all the supports till now. Okay, moving on to my presentation. So in this presentation, I'm just explaining the outline I'm going through. The first one will be an introduction, followed by literature, statement, objectives, proposed methodology, dataset description, experimental and result and analysis, conclusion and future work, and then the references I have gone through for this paper submission. So coming to the introduction, from the heading, you might have understood that the domain I have selected for this particular project was supply chain management. As everyone knows, supply chain management facilitates the flow of goods, services, and so when it actually deals with the goods, service, and information, any uncertainties in the capacity, demand, and cost will have massive impact on the supply chain management process. That's when the demand forecasting is so crucial in performance. Happening currently is the real world uncertainty is a great challenge to traditional supply chain management and its demand forecasting methods. Statistical analysis like time series and regression analysis have been employed for demand forecasting in SCM currently, but the limitation of a conventional numerous parameters influence the demand. And any partial understanding of demand variation are actually less adept at handling the nonlinear behavior, which is prevalent in supply chain dynamics. Because any data that we are dealing mostly in supply chain management is always having different factors, and it is moreover a nonlinear behavior. Okay, that's where the big data analytics comes to picture, where it uncovers insights of accurate forecasting. Also, BDA enables us for precise prediction on supply chain management. It always increases scalability, efficiency, and it makes the data processing easy. So, while coming to the literature review, all these papers I have gone through, I try to learn about what all are the different type of ML algorithms that we can use for different type of demand forecasting models, how we can deal with the different the supply chain data which is having seasonality on it, and what is an ensemble learning, how can I combine the results of two different ML models or algorithm to a single model and can come up with a more accurate or efficient prediction. So these are some literature papers I have gone through to gain this knowledge. Well, coming to the problem statement, as I already explained, effective demand forecasting is a critical component of supply chain management that has a direct influence in operational efficiency, the cost reduction, and the customer satisfaction. But however, the business often faces challenges such as inaccurate predictions, delayed responses due to market dynamics, and underutilization of advanced analytic techniques. So the problem was with the traditional forecasting approaches, which frequently falls short in handling large, complex, non-linear data sets or adapting to rapidly changing market trends, which was a shortcoming of this. Furthermore, the lack of integration between geospatial data and forecasting model limits the accuracy and relevance of predictions in location-specific demand scenarios. Additionally, business struggled to harness the full potential of big data frameworks. As everyone knows, big data was not part of most of the organizations. It was only accessible, or it was only used by big trades because of its cost and other reasons. So now, due to the help of cloud, if almost all adapt that big data framework. So advanced predictive analytics to achieve the scalable, efficient, and high-performing demand forecasting is now open for all the enterprises. Then coming to the ensemble method, we do an ensemble method with geospatial integration in big data analytics through promising remain underexplored. So this was not ever explored in this context, leaving a gap in optimizing forecasting accuracy and reliability. That was the reason why we tried to make use of big data analytics for the supply chain demand forecasting. And what is the objective of this project? The objective of this project was to provide a valuable insight and recommendations for business, aiming to enhance their supply chain demand forecasting and operational efficiency using predictive big data analytics. First, we started with a systematic study of various algorithms used in demand forecasting for supply chain management. Then optimized demand forecasting with ensemble methods. Also tried to integrate geospatial integration using clustering for improved accuracy. Also to leverage the big data frameworks for performance enhancement. Moving forward to the data set I have used over here, the data set I have used is Iowa liquor sales. As a brief description, this data set contains the spirit purchase information of Iowa Class A liquor licensed by product and date of purchase for almost 11 years, and it was approximately having 29 million rows. The total number of features in the overall data set was 24, but for this particular paper or project, I only made use of 10 that is mentioned over here. Also, I have performed the analysis of variance testing used to generate. ANOVA was performed to find the F value and P value to make sure that it is having a stronger relationship with target variables and making sure that statistically there are significant difference between the groups and it is not by a chance. So we were able to identify that features which we are going to use is having higher F values and lower P values. Coming to the proposed methodology, as I already explained, I have selected the input data set of Iowa liquor sales. Using that data set, first I have done a data pre-processing steps just to make sure that we are not having any outliers, the null values are removed. Also make sure there is proper scaling happen for the feature so that we won't be having any anomaly later. Then we moved on to the feature engineering where we have done the feature extraction and feature selection. In case of feature extraction, we have made use of the existing longitude and latitude data to come up with a new feature called as clustering with the help of k-means clustering technique. And for feature selection, we made sure that what all feature selection we have selected from the existing one will be helping us to come up with a better quality supply chain demand forecasting. Once we have completed with the data pre-processing and feature engineering, this prepared data set has then set for seasonality test. Anyway, supply chain management data set normally shows a seasonality by knowledge, but still we have done the seasonality test just to make sure that the going to use is seasonal. Then we have processed the data. The next first step I have done is a k-means clustering to come up with a new feature clusters for the geospatial integration. And to identify the optimal k-values, then this data has been fed to the different learning models for SARIMA, also the Prophet. Then we have done parameter optimization using the grid search to make sure that we are increasing the accuracy or the results of the learning model. Then we try to come up with the ensemble approach methods to combine the results of both the learning models and then a model evaluation using the MSC, RMSC, MI, and MAP. And it was integrated in a big data ecosystem using PySpark. And we come up with the prediction results. Seasonal decomposition I have performed. In the experiential result and analysis, the geographical similarities in demand patterns are identified by extracting the new feature cluster. As I explained, we have made use of the existing latitude and longitude column in the existing data set to come up with the clusters. So the geographical similarities in demand patterns are identified by extracting this new feature. Also, it helps in understanding the spatial patterns in the distribution of orders and can aid in optimizing the logistics and resource allocation. So just to make sure that we are doing the proper clustering and we are not making any computational mistakes, we made sure that the latitude and the longitude coordinates in the data set are standardized before going on with the clustering using the distance metrics. So here, currently you are seeing the result that I acquired from the first model, which is using k-means for clustering, grid search for hyperparameters and tooling. You can tell you can see that initially all the values were high while we was doing the normal one, but when I performed the hyperparameter optimization using the grid search, gradually the count came less and with a lesser MSC, RMSC, and MI and MAP with a better results. Moving forward, the second model was k-means for clustering, Prophet for learning, and grid search for hyperparameter optimization. Here also, initially the default value was really high, but after hyperparameter optimization, we were able to come less with the, and this particular model was outrunning the model 1 as per the results. Then we came up with the ensemble model approach. We tried to harness the results we achieved for both the model 1 and 2 from the hyperparameter optimization grid search to the ensemble model using weighted average, simple average, and linear regression. And as you can see the results over here, linear regression was having the lesser value and having more accuracy and efficiency in the result part. Reaching the conclusion of this particular paper and the project, we were able to commission predictive big data analytics for supply chain demand forecasting, the ensemble approach. The geographical similarities in the demand pattern is using identified using k-means, and the optimal k-value came up with Silhouette analysis. Also, the demand forecasting done using the SARIMA and the Prophet models. The optimal parameter tuning was done using the grid source. Furthermore, to enhance the forecasting accuracy, the ensemble method, simple averaging, weighted averaging, and linear regression was explored. Initially, the proposed model is experimented in 5-node Spark cluster deployed in the cloud for Iowa sales dataset, as I already explained. And we evaluated that using the matrices like MAP, MSC, RMSC, MAE, and MAP. The results suggested the SARIMA could achieve the lowest in MSC among the SARIMA models. During the hyperparameter tuning using grid search, improved the performance of k-means and Prophet model. Further, while we done the during the ensemble approach, it outperformed all the other techniques in terms of accurate metrics. So what is the future work? Actually, I was planning to do this project for my company where I'm currently working. So currently I'm working supply chain management. So this was like a real life issue that I was actually seeing during my working. So that was the reason why I came up with this particular topic. And as a future work, what we are planning is to employ other hyperparameter techniques like random search, Bayesian optimization, and genetic algorithm, just to make sure that we will be able to increase the efficiency. Also, to explore the integration of advanced machine learning techniques such as deep learning, the tools and techniques like LSTM and GRU for further model improvement. We are not ending up with just SARIMA and Prophet. We are going to explore it with a more advanced machine learning to check that we will be able to achieve more accuracy and efficiency in our demand forecast. Also, we are also planning to develop an interactive visualization dashboard and alert system for real-time monitoring and decision making, because end of the day, whatever we are doing or what we need to predict is actually for the business team. So it is really important that we should have an interactive visualization dashboard and alert system so that the business will get well alerted and it will be more easily understanding for them to take an actual business decision. So these are some reference books I have gone through during my project work to come up with this presentation. Yeah, that's all. That ends my presentation. Thank you once again for everyone for this opportunity.
Any questions from the audience? Since let's move to the next topic.
Thank you, Srini.
Okay, the next talk is on stock price prediction. It's paper 31. So we have Manimaran. Okay, Janth here from BIT-AP. So let's start.
Okay, good afternoon to all. My name is T. Jayant, under the research supervision of Dr. A. Manimaran, BIT-AP University, and the title of my paper is Enhanced Stock Price Prediction with Double Exponential Smoothing with encoder decoder bidirectional GRU using smoothing maximum unit activation function. So these are the contents of my presentation: introduction, literature, and data set description, proposed methodology, experimental setup, results, discussion, and conclusion, reference. So from coming to the introduction, involves buying, selling, and issuing public trading of shares is crucial for the stock market dynamics, and influenced by the behavior of stock trading. They may be positive or negative stock market, and politics, corporate performance, and global economy of complex factors are challenging to predict the stock price prediction. And from coming to the significance of accurate stock price forecasting benefits investors and reflects to economic health, and for using the advanced technologies ML and deep learning models to improve the accuracy of the stock price prediction using the SMU activation functions. For my proposed model, that is the hybrid model, double exponential smoothing ED by GRU using with the SMU activation function. So from the literature review, we reviewed to the traditional statistical models and the hybrid models, deep learning models, recent technologies also. From the traditional statistical models, simple exponential smoothing, Holz exponential smoothing, Holz winter exponential smoothing, and ARIMA. These are the getting the RMSE 72.84 and MAP 6.26%. From coming to the hybrid models, compared to the statistical models, hybrid models getting the more efficiency. Hybrid model, that is the seasonal ARIMA, combined with the double exponential smoothing, it will get the PICP score of 95.53%, and the deep learning models, that is the context ABT by LSTM CNN with 0.973 accuracy, and multiple TCN and TPA LSTM are get the more accuracy. For our proposed model, we use the general electric stock prediction with various time stamps, that is the daily, weekly, and monthly stock price prediction. From the data, we are first collecting from the data, we are clean the data for handling missing values and finding any outliers. After that, we are normalizing and scaling the data with uniform the same data. After that, we are exploring the data analysis for any trend, for that any outliers or trend in positive or based on the exponential exploring data analysis, we will get the how the data is presenting. After the pre-processing, we split the data into training and testing with validation and hyperparameter tuning. This is my proposed methodology. From collecting the raw data, we pre-process the data. After that, splitting the data. Then we will come to the hybrid model. First, we use the statistical model, double exponential smoothing. After that, encoder decoder. In the encoder decoder, at the hidden layer, we use the bidirectional GRU for free forwarding and back propagation for past and future values. After that, we are using the SME activation function to predict the hybrid model. For that prediction, we evaluate the metrics MAE, MSE, RMSE, MAPE, accuracy, R square, and tails U statistic, which are the forecasting evaluation metrics. When coming to the experimental setup, we as said that we first use the double exponential smoothing for the pre-processing stock price data to capturing the linear trend and smoothing fluctuations. After using for smoothing data, for using alpha and beta. For alpha, it is controls the level, and beta manage the trend smoothing. After that, we use the ED by GRU for nonlinear prediction model that captures the both past and future dependencies of the stock data. For using the SMU activation function, that is the SMU is of x equal to x by 1 plus e power minus x. This is the double exponential smoothing. Here we are using the alpha, two different type of alpha and two different type of beta with four possibilities compared to the actual data. For the evaluator metrics using to the three different type of data set, daily, weekly, monthly. Here the using tiles use statistics, our proposed model will get the lowest value. For the tiles use statistic evaluation matrix, it is lies between the 0 and 1. When the matrix comes to the nearly equal to the 0, our performance, that means our model get the best accuracy. When it far to the come to the 1, it will goes to not good. When from the results, for it is the using the General Electric stock price prediction data with daily and weekly and monthly data. When compared to the three data sets, daily data set is the get the good accuracy and prediction values. These are the evaluation metrics are used with compared with some deep learning models. From the discussion, our proposed model is getting the good accuracy based on the performance of evaluation matrix using the SMU activation function. When taking to the tiles use statistics, the lowest value of the General Electric daily data is 0.007 compared to the other weekly and monthly data. When conclude that our proposed model is demonstrate experimental accuracy in prediction daily data and combined with the double exponential smoothing and ED by GRU using the SMU activation function with achieve low error values and high accuracy. For my future work, we are effectiveness across the various financial data sets, and we are also planning to the attention mechanism also. These are the some selected references. Thank you. From Yahoo Financial, publicly available data, Yahoo Finance portal. From starting in that portal, from starting to that day, when we are downloading the day, that from that day. That means from.
Or BSc started?
Oh no.
So you have worked on around 45 years of data, is it?
No. That is 20 years data.
20 years.
That is only available in.
And you have taken every stock prices, every stock graphs into the system.
Yeah. Yes.
Right? Yeah. And based on that, if I am correct, you will be giving one particular input, and the model will be generating what will be the forecast for it for next one day, for a week, and for a month.
Yeah, yes. But we are actually predicted only training and testing, not for future. That is the future work we are working on that.
Good. Thank you.
Thank you.
It's a very nice work. Nice presentation.
It is the hybrid activation for combined with the relay activation and softmax activation function, which is better than the both. Compared to the time complexity, when we're training the data set, it will less the time complexity.
Your efficiency in terms of the time complexity only.
Yeah.
Did you try any other SMU functions, like just other than e to the x divided by 1 minus that function? So did you try some other function as well?
No, not this. This one. Yeah. That is. This is 7 features around and 35,000 variables. Yeah. Daily data you will get the good accuracy compared to the weekly data and monthly data. Daily data get the good accuracy. Thank you.
for your presentation.
Thank you for patience listening.
Paper ID is 52 and yes, it's real-time pothole detection system. Please go ahead.
Good afternoon to everyone. I'm Ajay from Vasvi College of Engineering, and in the guidance of our professor and our assistant professor, we did a project, real-time pothole detection. We are with SSD, and if we come to basic abstract of our project, it's in India we can see potholes as a major issue in on the roads because there are many accidents that are happening due to potholes, and after even though they are doing their best to repair them, if after every rainy season we can again see the new potholes on the roads. It's it's a continuous issue in our country, and to solve that we developed a model, a real-time system using SSD to identify the potholes, and that can be updated on a Firebase where government officers or any user can also update the location of the pothole and with an image, and the officers can verify the pothole, and they can issue some solution to clearing the pothole or some other solution. And this study is centralized it's creating a platform of pothole detection using Neo 6M GPS module and ESP32 camera modules. And the Neo 6M GPS module is used for tracking the location of pothole, and ESP32 camera modules are used to extract the pothole image and send it to the model. The main challenge that we are addressing is road damage, which is road damage detection and reporting. So by using this model, we can easily we can simply give it to traffic cameras, and it can detect the pothole, and it can update it in the Firebase our database, where anybody can access and see where the potholes are present. And if any user want to we have also integrated it with the Google Map. So if any user want to go on from one location to another location, he can access this and see how the road is, and how he can easily travel from one location to another location without any without any potholes on the roads. And the planning will be easier for drivers. The main thing about this system is to ensure road safety and minimize the vehicle damage and accidents. For this project, we basically did literature survey based on the papers, papers on SSDs, and integrations of SSD with ResNets. So what we came up with is how ResNet can ResNet 34 can be integrated with SSD to easily extract features and give more accuracy, and how SSD is better from faster RCN when compared to because faster RCN is a two-stage detector, whereas SSD and YOLO, all these are one-stage detectors. And why we choose SSD is basically it excels in balancing speed and accuracy when compared to YOLO models. And SSD has gone an extensive study and improvement. Various works have optimized its architecture, and what we added is ResNet for extracting the features, and added it the extracted features are sent to SSD for evaluation and creating bounding boxes. And in the dataset we also added data based on changing the lightning and adding more shadows to the data set, and also we also transfer the images from color to gray light so that it can be visualized as the model can be trained on diverse data set. And we also adjusted hue conditions or everything to make the model not to overfit and have diverse conditions to diverse conditions. It can identify the potholes. The main steps in our proposed work is first data collection and pre-processing, and framework and architectural model, and we splitted the data we have collected into custom data sets. And after training the model, we tuned the hyperparameters to get more accurate results, and we integrated it with Google Maps for analyzing damages that are reported. So the basic methodology of our project is to collect data collection and labeling the images, and we are basically training them. Like before training them, we have augmented the images, so we can get more images from the present ones. And in augmentations, we used augmentations module Python library, and we split the data set into training, testing, and validation data sets, which are like 70, 15, 15%. And after training the data set on result model, we given that we transfer the learning capabilities of that model to SSD, and we easily predicted the bounding boxes. And in real time, what will happen is EST32 like a ESP32 camera module captures the images, and it will give the model to Resident 34, which extracts the features present in the model, and the extracted features are given to extra feature layers, which creates the bounding boxes. Like the SSD creates the bounding boxes in the model, and the models, if they predict a pothole is present in the given image, it will update it into the Firebase. And after that, the camera will be off for it will be turned off for 24 hours, because we don't want to send same image to the database multiple times. And by using Neo 6M GPS module, we are also updating the location in the database for clarifications. And the data collection and pre-processing in this step is like we collected data set from Kaggle, which has a 700 plus images. We labeled the images with using label me, and stored the labels in XML format. And these 700 images are like we did augmentation and increased the number of images from 700 to 2000 for training purposes. And for augmentation of images, we basically used augmentations of data sets, where we did different features on different types of, different things on different types of images. For some of images, we did random cropping, extracting some of the features and cutting some of images. And we also used grayscale conversion to transform images to grayscale for easier for making the model diverse. And saturation adjustment and brightness adjustment are used for different brightness, because in real time, at any time the model needs to predict the pothole. And hue adjustments, shadow adjustments are done to give it a realistic effect. And in nighttime simulations also, nighttime images are also given to the model for the model to work in diverse conditions. And the framework we used for this paper is to model is PyTorch, because SSD is basically developed on a TensorFlow. We want to try it on different framework, and we tried it with PyTorch. And the architecture is ResNet, which is for a feature extraction and identification of features, and which is given to model, which is SSD. And by training the SSD model with on our custom data set, we trained it on different optimizers and learning rates. And initially the model, when we trained the model, it used to give us a less result, but by hypertuning, we got the wanted results. And the best results are given when we used SGD loss function with a learning rate of 0.0005 and a momentum of 0.1. The result we have achieved is 88.676 map score, and with a train loss of 0.6764. And we also trained the dataset on different models for a comparative study. And from what we trained on YOLO mini models and nano models, and large models and extra large models also, the overall results are not as satisfied as for a SSD model. So we choose a SSD model for the prediction in real time. and these are the results we obtained in our training of models. And these are different hyperparameter tunings. Like in the first image, we can see the momentum we took was 0.1 and our learning rate is 0.001. And optimizer we took was Adam optimizer in the first image, where we changed the momentum and optimizer in second one, and the optimizer is again changed in third image. And the best results are occupied in fourth one, like 0.1 momentum and SGD optimizer with a learning rate of 0.0005. These are the images like results. Here, as you can see, the potholes are detected with some confidence levels, and they are updated in the website here. And when we click on the location and the map, it will show where are the potholes present in the location, like a route, and officer can easily send some members to repair or do something on that potholes. And this is the like interface where we can where the officers can see present like where the data is from, and how the situation is, and also like on the map they can see the location, and from camera ID they can notify that like from which area the images came which image came from. And the conclusion of this this is my the basically the conclusion is we did a resonant model integrated with SSD for high accuracy predictions, and there may be in future there may be some new models where which have more accuracy, which can be easily predict the manners, and I guess that's the future scope of it. The basic software and hardware requirements of the projects is Python 10, and the main libraries we used for capturing the images are OpenCV, and PyTorch is used for model implementation, whereas the augmentation and label me are used when during augmentation and labeling of the images. SSD is the basic model of our project, and Google Colab is used. Generally, we used Google Colab, but we can also replace it with a system with GPU, working GPU. And the hardware requirements are ESP32 and ESP32 for data transferring, and Neo 6M GPS module and a TTL for data transferring and capturing the location.
So my question would be, how exactly the single shot detection is coming into play? Like why is it better than other say, one level learners?
So if we want to use, we can use fast CNN or RF CNNs. But if we use that, time to predict the image where porthole is present will be more compared to one-stage detectors like SSD and YOLO. And in the one-stage detectors, we have compared the SSD is giving high performance compared to others. Like YOLO, we basically did it on different types of models. YOLO V5 mini models and small models and nano models also. And we also did it on YOLO V8 models. And based on our results, the more the model that's giving highest accuracy is a SSD model.
Thank you. Talk of this session is from IIIT Lucknow. Akanksha Singh is presenting the talk, so it's air quality and pollution prediction of urban areas.
Good afternoon, everyone. Am I Good afternoon, everyone. Am I audible? Good afternoon, everyone. My name is Akansha Singh. I'm from IIIT Lucknow, research scholar. Thank you so much for giving me this opportunity. Today, I'm here to present my paper that is based upon data analysis with model explainability for air quality and pollution prediction for urban areas using edge networks. Moving on to the first slide of the presentation, we have the outline of the entire PPT. We are going through it. The first slide will be from the introduction, research gaps and objectives, methodology, system model, experimental analysis, conclusion and references. Moving on to the very first slide, we have introduction. Basically, air quality prediction is very crucial for safeguarding the human health, for protecting the environment and reducing the impact of the pollution on human health and economic stability. Accurate air quality prediction is very essential for public health because in the urban areas, already the air quality is at a very alarming rate due to rapid industrialization and urbanization. And accurate and local predictions of the air quality is very helpful for mitigating all such issues of health analysis and the economic stability of the nation or the local area. Moving on to the continuous slides, we have associated problems and the current state of knowledge in the terms of air quality. So as I was saying that we have associated problems with the air quality. The very first problem which we generally face is the current ML models struggle to predict the air quality accurately in the urban areas because the smaller section or the microenvironments of an urban area has different contaminant levels, have different geographies and meteorological conditions. So each and every smaller subsection of an urban area has different types of problems that are associated. Because of that, the standard ML models are not able to predict the the smaller microenvironment air quality. The second challenge which we generally face or the associated problem with air quality is that the standard ML models are generally trained on the generic data, not on the precisely on the local data of that particular microenvironment. Similarly, the resource constrained edge environments or the edge network are not able to handle large amount of data or large dimensionality of the data because of constraints of computational constraints and storage constraints. So because of this, these are the basic associated problems that are generally seen in most of the research and the papers that are being present in the field of air quality. The current state of knowledge states that the existing model have large scale generalized data set that are usually processed in a centralized location of cloud processing, and the new approaches like data fusion or localized edge network computing are being accepted in the field of air quality prediction also, but the challenge of feature extraction and the multiple dimensionality of the data still exist in most of the papers. Therefore, we have suggested a hybrid model of the entire system in which we are going to use the cloud and edge based computation that will be hybrid in nature. Moving on to the next slide or the next section of the PPT, we have research gap and objectives. Primarily, there are three research gaps that are being identified while going through the literature surveys. The very first is limited computational capacity of the edge network. All the edge networks are having limited computational capacities as well as the storage capacity. Similarly, local versus public data. Generally, what happens is that we tend to train the model centrally on the cloud with the public data, but the microenvironments have different type of contaminants and have different type of geography. The similar city itself can have different types of pollutants within the city itself. Therefore, localized data should be used for prediction. Third thing is the third research gap that is being identified is insufficient data for robust model prediction. We generally have a similar type of data from a similar location and therefore the data is biased sometimes. Therefore, having different data from different time zones or different area of a city is very crucial and important. So these are the three research gaps that we have identified. On the basis of these three research gaps, we have made these three research problems and the three hypotheses that are going to resolve or mitigate these problems. The very first was insufficient data. For that, for the removal of insufficient data, what we have done is we have used the data from APIs. We have fetched the data from two APIs and the public data that was available on Kaggle. We have used data fusion methods or basically data concatenation to have to address this issue of having limited or similar kind of data so that we can remove the biasing in the data. The second hypothesis states that the standard ML model were trained on the cloud itself and the prediction was made on the cloud itself, not addressing the microenvironments. Here what we have done is the standard ML model will be trained on the cloud, but the feature extraction methods will be implemented to identify the key features, and those key features will be deployed on the edge environment or the edge network, so that there the local data can be collected using sensors, and there we can have that proper implementation and prediction at the edge, which will be conducted in the future aspects of the project. The third aspect that has been as a problem statement that has been identified is that there is lack of transparency in the overall prediction. For that, for removing this issue, we have used explainable AI for removing the for adding transparency and adding the interoperability between the decision making and addressing this entire issue. Moving on to the next slide, we have methodologies. Basically, we have three problem statements and therefore three contributions. The very first is data fusion, for which we have used API data and publicly available data. We have fused the data, and the equation for that is given here, that the total data, that is, we are going to create the test bed on the basis of the public data and the API data. The details are given on the further slides. We have been collecting these data, and we have fused this data all together to form a generalized test bed, and this test bed is further used for this test bed and further goes for data pre-processing and cleaning the inconsistencies, cleaning the data set, and removing the missing values. The second contribution states that the overall prediction or overall training of the initial standard models will be held on the cloud, and the feature extraction methodologies will also be held on the cloud itself. For this, what we have done is we have used 4 standard ML models, that is KNN, SVM, random forest, and decision tree. These are the 4 basic models, standard models, which we have used. We have trained these models on the data that we have collected after data fusion, or we have created testbed after data fusion. Once these models are implemented, we have implemented the feature extraction technique, that is mutual information. But mutual information is the method by which we identify that what are the particular parameters that are going to impose more effect on the prediction or the resultant we are going to target. So using this mutual information method, we have identified the key features that are more important for this prediction. After these key features are identified, we are going to train the models after removing all the unnecessary parameters and features, and only the necessary or selected parameters are used to retrain these models, and the models are compared before and after on the basis of the performance matrices, CPU and memory utilizations. And post this, the best models and the best model and the best parameters or key parameters are transferred to the edge environment. In the third contribution, what we have done is we have used explainable AI, that is SHAP in this particular case, for maintaining this, that the entire working of our project or the entire flow of the project is correct, for making this entire transparency in the decision making. SHAP tracks the features like SO2, NO2, etc. All these features, it tracks all the features and identifies that which particular features are posing more impact on the feature, on the prediction that we have made finally. So a little bit of detail of SHAP. Basically, SHAP is a explainable AI method. There are 2 methods, SHAP and LINE. We have used SHAP here. And what SHAP is doing, what is the relevance in our model? SHAP is doing 3 things here. First, model transparency. It is providing the transparency within the layers of the model. The second thing is feature importance, which features which we have identified using mutual information are the same features that are identified using SHAP. And the third is model validation. We have used SHAP for 3 things here. Moving on to the system model, this is the architecture of the system model. If you can see, first of all, we have done data fusion of the API data and the publicly available data from the Kaggle. We use this data to train our standard models, that is KNN, SVM, random forest, and decision tree. Post this, we have used feature extraction methods, and after feature extraction, we have identified the key parameters and retrained our model. After retraining the model, we have compared both the models before and after, like retraining on the basis of performance matrices, and the best and optimal model with the optimal parameters and key parameters are sent to the edge network, which will be sent in the future to the edge network, where the local data will be collected using sensors. This part is not implemented as of now. It will be implemented in the later on stages. The third part, that is implementing the entire process or entire working on the edge network using this, collecting the data using the sensors. So this is the overall system model. Moving on to the experimental setup and data set, we have used these 4 standard models, that is KNN, SVM, decision tree and random forest. The performance matrices are F1 score, recall, precision and your this recall. And in the test bed we have 3000 records, and the data of the test bed which we have identified as the prime parameters: CO2, CO, NO2, SO2 and PM10. According to a report published by WHO in 2002, it was already identified that PM10 is a primary pollutant that is causing approximately 20,000 lakhs of deaths each year just because of PM10, that is particulate matter 10. Moving on, we have trained the data, and we have divided the data into training and testing beds, and we have trained the data, and finally we have used SHA to implement the transparency. This is the resultant. There's no major there's a very slight improvement in the entire working. If we can see that there is a very slight improvement in the terms of accuracy, precision, recall and F1 score in mostly all the algorithms which we can see here. The overall improvement is not that big enough, but yes, there is a slight improvement which can be further removed, or which can be further more enhanced in future terms. Moving on to the last part, that is conclusion. We have created this entire study as a basic foundational process to create a robust model that will be having the localized data set at the edge network using Raspberry Pis and using sensors later on. This is the foundational step. We will be completing this project later on. And other than that, we have used API data and publicly available data sets. We have created this entire proceedings with the help of data pre-processing and data consistency and quality. Further, we have used this approach to ensure that the resultants are unbiased in nature, and there is high accuracy and precision in our overall resultant. The future scope of our project relies in federated learning. We are planning to implement federated learning in the entire proceedings, where each of the individual local edge network will be collecting the data, it will be performing the analysis, and further all the entire data will be sent onto the cloud so that we can use transfer learning or federated learning on the cloud itself. Moving on, the next future scope will be emerging technologies that I have already told that we are planning to use IoT and AI in the upcoming stages of this project. Scalability, we can scale up this project to a much higher extent of a bigger section of an urban area, and energy efficiency is the next step which we are planning to confirm. That is, we are going to analyze what are the latency issues that we are going to face between the cloud and the edge. Along with that, we are going to analyze that what are the energy efficiencies and how we can maintain the energy in the entire working of the project. These are the list of references which we have gone through while creating this entire project as of now. Thank you so much for your patience hearing. Actually, while doing this, while creating the test bed, we had we had major constraints, like we had to take the data from a similar location, which was not possible in the case of publicly available data set. And similarly, that was the case with APIs also. So for the foundation,
So this ends this session, and we will be having the closing session of this conference on today at 4 p.m. So please be here at 4 p.m. today, and Professor Srirama will give the closing remarks of this conference. Thank you. So we have another announcement. There is one tutorial ongoing on F6 upstairs. So if you are interested, please visit F6 and you can be part in the tutorial. Thank you.